Hello. Right, we're here to do part 2 of the photoelectric effect. So yesterday, last time, whatever, I introduced you to the photoelectric effect, Einstein's clever Nobel Prize winning notion. Let's look at it in a bit more detail and have a go with some of the equations. Basically, starting off though, a little starter activity to keep you out of trouble. Basically, what is the energy of the following sources? A wavelength, a lambda emitting light of wavelength 600 nanometers, an X-ray source giving X-rays of wavelength times 10 to the minus 10 meters, radio signal wavelength 3 meters, and then the second part is, can you convert the following to joules? So pause and have a go, and then I'll give you the answers in a second. Turn my calculator on. If you need a little bit, remember E equals HF, or E equals hc over lambda. H is Planck's constant, 6.63 times 10 to the minus 34. C is the speed of light, so 3 times 10 to the 8 meters per second. So there we go. So the first one, we've got 6.63 times 10 to the minus 34 times 3 times 10 to the 8, 10 to the 8, all over 600 times 10 to the minus 9. Gives us 3.3 times 10 to the minus 19 joules. Then for the next one, we just basically substitute from the bottom, 663. So I'm just going to go 1 times 10 to the minus 10. Uh, 1.989 times 10 to the minus 15, something small, and the last one is going to be a big one. Gives us 6.6 times 10 times 10 to the minus 26. And convert these to joules, so you do 1 electron volt times 1.6 times 10 to the minus 19 is 1.6 times 10 to the minus 19. Then it's 10,000 times 1.6 times 10 to the minus 19, and 5 million times 10 to the minus 19. Easy, you can do that. Okay, so yesterday we did a little bit, let's do a review of the old photoelectric effect. So remember, we have a piece of metal, something like this, and inside the metal we have little electrons are on the surface, and then if you get the right frequency of light come in, these electrons are released. This is basically ionization. And you know ionization works if you remember things like the electromagnetic spectrum, radio, micro, infrared, visible, are non-ionizing. They don't have enough energy to release electrons. Ultraviolet, X-ray, gamma are ionizing, and it's this is why one's ionizing and the other one's not ionizing. The ionizing part of ultraviolet and X-ray and gamma means each individual photon has enough energy, which we can work out from E equals HF, to free an electron from the attraction that it has from the nucleus. So there's a nucleus, and the electrons exist in these kind of orbitals, shells, clouds, depending on what part of science you're looking at, and they're bound because the electrons are negative and the nucleus is positive, and they're bound. But the further away you get from the nucleus, that kind of attraction is reduced, because It's directly proportional to, well, actually inversely proportional to that. But basically, the further away you go, the weaker that attraction becomes. And if you get them far enough away, they are then classed as free electrons. They can be free. And if you free them, you have ionized them, you remove them, and you've made the thing an ion, and the electrons are free. And that works when you have photons that are energetic enough to give the electrons enough energy to jump free. If the photons are not energetic enough, say green comes in, it hits the electrons go, oh, I'm going to escape. No, I don't have enough. And they get pulled back in, and so they cannot escape from the surface of the metal. And I think I mentioned at the end of last lesson, we have E equals HF. F0 is called the threshold frequency. So that is the minimum frequency required to release an electron, a photoelectron, from a material. Now that changes the material. Zinc has a particular threshold frequency, it's like ultraviolet, whereas other metals have different threshold frequencies with different metals. Sometimes you want it to refer to as the frequency, but if we times that frequency by h, Planck's constant, F0 times h, we have something called E, a particular E, which is otherwise known as the work function. The work function is the smallest amount of energy required to release an electron. So F0 is the threshold frequency, the minimum frequency of a wave that will release an electron, whereas if you times that threshold frequency by Planck's constant, you get an energy, and that energy is called the work function. And the work function is the energy required to release an electron from the surface of the material. So the work function and threshold frequency are basically talking about the same thing. One talks about it in terms of energy, and the other one talks about it in terms of frequency of the photon. Okay, so this is actually the Einstein equation, Einstein's photoelectric effect in the equation, and we have two different things. So, for example, let's look at this. So it basically says the kinetic energy of the electron is equal to the energy of the photon minus the work function, the energy needed to escape. So if your photon HF has this certain amount of energy, then basically, if HF is greater than the work function, the electron will be free. But if it's not greater than the work function, the electron won't be free. But if it's equal to the work function, HF equals the work function, which is basically saying HF0, the electron gets free. There it is. It goes, whee, I'm free. And then it just sits there and doesn't really know what to do. Like at the end of Finding Nemo, where all the fish are in the little bags and they've escaped, and like, okay, what do we do now? It's kind of like that. They've escaped, they've put all their effort into escaping, and now there's nothing left. But if the it doesn't want to delete that. That is interesting. But if the photon has greater energy than the work function, that means there's a little bit leftover energy for the electron, and the electron then can do stuff. The electron can fly, it can run free. How do we describe the energy of a moving electron? We talk about it in terms of kinetic energy. Things keep going to this crazy highlighting. So another way to describe this, or another way to write this, is the kinetic energy of an electron is equal to, so this is Ke of electron, and it's equal to the energy of the photon minus the work function. Now, if the work function is higher than the energy of the photon, that means the electron will have negative kinetic energy, so it's not escaping. If the work function is the same as the energy of the photon, it ends up having no kinetic energy. But if the photon has more energy, than the work function requires, then any leftover energy goes into the electron, and the electron can use this to go and fly away and do lots of cool stuff. There's a little animation. No, there's not. There's a little thing. Let's time for you to have a go doing some questions. What we'll do is, if you can practice this question, and then I'll show you the answers, and then once you've done the answers, you can... Shall I do a little work through with you? Shall I do a little... I'll help. Let's move this over here and put that there. So I'll give you a helpful example. Calculate the frequency of incident radiation of an electron is emitted with an energy of 3 electron volts from a metal surface at a work function 3.5. So this is saying Ke equals... I haven't done this. Where's the mouse? Ke is 3 electron volts, 3 eV, and the work function was 3.5 electron volts. Okay, and it wants to know what F is. Okay, so first thing, let's convert these to what's it called? Joules. 3.5 times 1.6 exponential minus 19. So we've got, this is 5.6 times 10 to the minus 19 joules, and this is 4.8 times 10 to minus 19 joules. If we look at the equation, so we've got Ke equals HF minus phi. So if we do Ke plus phi, that would equal HF. Move this up a bit. So kinetic energies plus the work function gives us this. So we do Ke plus phi all over H equals F. So 4.8 plus 5.6 times 10 to the minus 19 all over 6.63 times 10 to the minus 34. 4.8 plus 0.6 minus 19 divided by 6.63. Minus 34 gives us 1.57 times 10 to the 15 hertz. I really hope that's an option. Oh, 1.57. Yes! It is an option, thank goodness. Let's have it write it down. Calculate the right hand side. Oh, we don't need to do that. Right, there we go. Why don't you have a go on this one? So here we go. So this time, the frequency of the incident radiation, we've got electrons. So they've now got 5 electron volts. The work function was 3.2 electron volts. So what is the frequency of this? I'll work it out at the same time as you. Check that. So, if you need to pause, and if not, let's see whether you got it correct. Oh yeah, 1.98. Basically, first thing to do, showing us working. Work out the right hand side. Oh, damn it. Add the 2 electron volts together, convert it into joules, and then divide the joules by the Planck's constant, gives us 1.98 times 10 to the minus 19. Go on, do another one. Excuse me. Should probably do it too. Ooh. Got an answer, different answer. Hang on. It's asking for the wavelength. Whew. That's why I did that wrong. So that gives us the frequency. So, yeah. panicked because I couldn't work it out, but it was asking for the wavelength instead of the frequency. So same process, you work out the energy, you divide that by Planck's constant, and then you convert the Planck's constant divided by the frequency into the wavelength. Speed of light divided by the frequency. And one more. Calculate the wavelength, another wavelength one. Do it. 10. Should give you this one. Yeah. Exactly the same process before. Convert the electron volts into joules. Divide the energy in joules by the Planck's constant, and then you do the speed of light divided by frequency, gives you the wavelength. Alright. Move this out of the way. Okay, and probably should be a little bit more for this, but actually what I'm going to do is actually I might just leave it at that, and then we'll do some more next time face to face. There's one more little animation. Let's do this. Right. So here we have Einstein's photoelectric equation and work function. So energy is equal to hf, which is Planck's constant. So this is just another way of doing it. It's the work function plus the kinetic energy. So if we click on hf is the energy of our photon that comes in, coming in. Frequency of the photon multiplied by Planck's constant gives us the energy. The work function is the minimum amount of energy required to release the electron from the surface. And Ek is the kinetic energy the electron will have. Basically the difference between the energy of the photon and the work function, as long as that's positive. I feel like I've given you lots of information very quickly. I might add a couple of questions at the end just for you to do once you watch this video, so check for that, and if I haven't, easy. Have a nice time, and I'll see you next week, hopefully, when I'm no longer COVID-y. Bye!